Okay, so this is the first example of a series of examples with different methods where we look at one simple beam exposed to uniformly distributed load Q. As you know, the strength of this beam can be described as the section modulus times the yield strength, and the load on such a beam is QL squared divided by 8. That means that the limit state or safety margin can be written in the form of resistance minus load, which would then be like this. So here in this first example we are looking at design by limit state method, and then of course we need to define the different values: section modulus, yield strength, the load Q and the length. And in addition we need material safety factors and load safety factors, which are typically taken from standards. The utilization of the beam can then be calculated as load divided by the strength, and if the UC or utilization coefficient is less than 1.0, which indicate that it's sufficiently safe. And note that we here have included the safety factors for load and safety factor for the material. To do the further probabilistic analysis, we have to determine the distribution for each of these parameters. We can assume section modulus is normal distributed with a COV of 11.8% in this case. Normally the geometric properties are chosen to be according to the mean value, and the standard deviation is 11.8% of this. The yield strength is normally modeled as log normal with a COV in the range of 5 to 10%. Here we have chosen 10%. The characteristic value that is given in standards is normally chosen as the 5% lowest value. If we start looking at the normal distributed, how would we determine the mean value and standard deviation if this was normal distributed, which is a little bit easier? We know that the characteristic value is the mean value minus, since it's the strength parameter, a k value times the standard deviation. We don't know the standard deviation and the mean value, so we divide by the mean value on both sides. With some manipulation, we get that the ratio between the characteristic value and the mean value is 1 minus k times the COV. And then we can calculate the mean value as the characteristic value divided by 1 minus k times COV. And then we know, since we now know the characteristic value that is given typically in standards and the COV, which we have to assume, but there are guidance that we can find for typical COVs. After the mean value is calculated, the standard deviation can of course be calculated as the COV times the mean value. For the 5% low value, the K factor for normal distributed variables is 1.645 according to normal distribution tables. And then we can see that we can calculate the mean value from the characteristic value of the yield stress as we have found earlier, divided by 1 minus 1.645 times 0.1, and then the mean value is 609. That should be compared to the 509 that was used as the characteristic value, so we can see that the mean value is significantly higher than the characteristic value. The standard deviation is 60.9. However, as we said in the beginning, this is a simplification by using the normal distribution. So if we want to use the log normal, as we expect to be correct for this type of problem, we need some definitions of the normal distribution first, and then we can calculate the mean value according to this formula, which I will not explain here, but it can be derived from the normal distribution. And we can calculate the mean value giving 600 megapascal, and the standard deviation will then of course be 60 megapascal. The next parameter is the loading, and if we, for example, assume that to be Gumbel distributed with a COV of 36.5% and a characteristic value assumed to be the 50-year value, or the value with a P of 0.98. For example, distributed variable, a similar ratio between the characteristic value and the mean value can be determined and described by this formula. And then insert the relevant values here, probability level that we are searching, and 0.365 as the COV. And we get 2.5 kilonewtons per meter as the mean value. The standard deviation, 0.365 times this mean value, giving us 0.9 kilonewtons per meter. And we can also see here the mean value is of 2.5 is significantly less than the characteristic value of 4.886. The last parameter is the length, which we again assume to be normal distributed with the mean value as similar to that used in design, and a COV of 1%, which then gives us a mean value of the 10 meter used in the design calculation and a standard deviation of 0.1 meter. So then we should have the necessary values that we need for doing some probabilistic or structural reliability analysis of this problem.